Okay, note to self, learning about parasitic worms right before dinner. Bad idea. Blech. But on that note, what am I hungry for? Oh, I know. Huh? Did I lose my pasta maker? Oh, well that sucks. How do I make spaghetti without... Hello, fellow wanderers. I'm your arbiter, and welcome to the Wanderer's Expanse. In many ways, black holes represent the upper limit of phenomena in the universe. What exactly goes on inside is still somewhat speculative, but today we'll be taking a trip to the extreme environments that exist around them and explaining why something that emits no light at all is actually the brightest thing in the entire universe. And also making pasta. That too. But first, let's talk about how you find something that you basically can't see. So, how do we find black holes? Well, the short answer is by observing what's around it. You can look at how other stars are moving to see if something invisible is pulling them around, see if light is being bent with no observable cause, or if a binary star system is emitting a lot of X-rays, and other methods. For a long time, black holes were predicted by our understanding of physics, but hadn't been directly observed. One of the first candidates for a stellar mass black hole was Cygnus X1 in 1972. When a star, commonly a white dwarf or a neutron star, feeds on its neighbor, it tends to emit a lot of X-rays. However, after watching Cygnus X1 for a while, some unusual patterns remained. So you're saying it's too massive for a white dwarf? Yep. And there's no supernova remnant, so it's probably not a neutron star. Did you remember to carry the 1? While the debate was still up in the air for Cygnus X1, eventually many more observations of different objects and places all seem to conclude the same thing: that our universe is full of holes. The strongest evidence came in 2015, when the team at LIGO detected gravitational waves coming from 2 colliding black holes. Actually, let's make a quick stop there. Welcome to the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. So firstly, what are gravitational waves? Well, unfortunately, they're not exactly the kind of waves you can surf. Aw, man. Instead, gravitational waves are the distortions in space-time caused as objects accelerate through space, a bit like the wake of a boat. As 2 massive objects, like black holes, orbit each other, they continuously send out these oscillating waves, speeding up the frequency as they get closer to each other, and eventually collide. That collision would produce a very specific wave pattern, which would tell us if it was just a couple of normal old neutron stars, or if it was something like a black hole. The only problem is, by the time these gravitational waves reach Earth, the effects are so minuscule that, unless you're the size of an atom, you're not going to be able to feel the effects. Oh no. I'm gonna be sick! But how does LIGO detect these minute ripples in space-time? I mean, it's kinda in the name. It's lasers. It's always lasers! Put simply, LIGO splits a laser beam down 2 4-kilometer long arms. After some enhancement using mirrors to increase the power of the lasers and the distance they travel, the split beams reconverge. If everything is as it should be, the lasers should meet each other with the exact same frequency and energy, canceling each other out so no light is actually detected. However, if a gravitational wave came along, it would essentially stretch the arms unevenly based on where it was coming from. This would mean the lasers wouldn't travel through the same amount of space-time and wouldn't completely cancel each other out anymore, allowing some light to be detected. The more distorted and out of sync the lasers are, the more light detected and the stronger the gravitational wave. And so, in 2015, LIGO finally detected the waves of 2 orbiting black holes merging into one. And when translated into sound, those waves make this terrifying noise. Truly bone-chilling. And finally, after combining the power of several radio telescopes all across the world, the Event Horizon Telescope project was finally able to take a picture, sort of the black hole at the center of the Messier 87 galaxy, aka M87. And later on, the black hole at the center of our own Milky Way galaxy, Sagittarius A star. But you know, I wish they could have gotten my good side. So, how do you form a black hole? Well, all you really need is enough matter or energy in a small enough package, and boom, you get a black hole. Oh, actually, welcome to the universe right after the Big Bang. Pretty nice production quality, I know. Now, it may look like an all-white void of nothingness, but if you look really, really closely, it's still an all-white void of nothingness. Everywhere you look is superheated matter packed really close together, to the point where you wouldn't actually be able to see it, because any light emitted just runs into more particles. In the first second after the Big Bang, some parts of this cosmic soup may have been dense enough to form black holes off the bat, called primordial black holes. They're probably around here somewhere. If only I could see them! The bottom line is, anything can become a black hole. You just need to compress matter to a stupid degree so that it's smaller than its Schwarzschild radius. The most certain way of forming a black hole is by the collapse of a really big star, with roughly 20 times the mass of our sun. While this is a pretty complex process, as it turns out, the important thing to know is that after a certain amount of time, stars run out of fuel for fusion reactions. This means that the star is basically crushed under its own weight, causing its core to collapse into either a neutron star, or, if it's massive enough, a black hole. This process occurs at the end of a massive star's life, which can take millions of years. But who's got that kind of time? So I kinda, sorta, had an idea. Now remember, don't try anything you see here at home. I mean, I don't even know where you'd find a hammer this big, but anyway. So, now that we have our own, let's discuss why black holes are a lot brighter than you might think. Around a black hole, you may find a spinning ring of gas and dust called an accretion disk. Here, as matter falls inward towards the black hole, it converts potential energy into kinetic energy and speeds up. As all the particles rub together and smash into each other at unimaginable speeds, it creates an immense amount of heat and light. So, you know the sun, right? I'm gonna assume you said yes. By fusing hydrogen into helium, it converts roughly 0.7% of the mass involved into energy by E = mc². On the other hand, by converting potential energy into kinetic and other forms of energy, a black hole's accretion disk can produce between 6 and 42% of an object's mass in energy, depending on how fast the black hole is spinning. So yeah, accretion disks are incredibly energetic, but how energetic are we talking? Well, let's go back to Messier 87 versus our sun as an example. Our sun's bolometric luminosity, or the total energy across the electromagnetic spectrum, is equivalent to 3.8 times 10 to the 26 watts, of which only a small fraction actually hits Earth. This is already an unbelievable amount of energy, of which a small fraction powers basically all life and weather on Earth. So how much stronger is M87? 10 times stronger? 100? No. M87 outputs an estimated bolometric luminosity of 2.7 times 10 to the 35th watts, meaning it literally shines with roughly the energy of 700 million suns. What? All this energy released means that a black hole, or at least what's around it, can glow brighter than a star, brighter than entire galaxies in the case of quasars. So yeah, you might want to grab your sunglasses. Or a new pair of eyes. I should have some extras lying around here somewhere. But the fun doesn't end at accretion disks. And yes, I said fun. Along the axis of rotation of a black hole, you'll sometimes find two jets of particles shot away from the black hole at nearly the speed of light. These go by a few names, but are often called relativistic jets. So, you know the feeling of a nice, slow breeze hitting you on a warm spring day? Well, now imagine it hitting you at the speed of light. Yeah, what we're talking about here is less fireball, less laser, and more... I cast everything in that general direction! In many cases, the sheer kinetic energy of the jet can be even more powerful than the accretion disk. Like, a lot more powerful. In the case of M87, like, almost 100 times more powerful. So yeah, probably not something you want to get in the way of. Now, if you'll excuse me. Matter is shot out with such speed and energy that not only does it escape the black hole, not only does it escape the entire galaxy, but in some cases it can form clouds that stretch out for millions of light years, or hundreds of galaxies long. Again! But okay, let's say for the sake of argument that you survive being blasted by enough radiation to turn your dust to dust. What happens if you got even closer to a black hole? Well, the short answer is tidal forces. The long answer is what happens when a body is torn apart in various fun and exciting ways by gravity. Tidal forces are the uneven pull on different parts of a body in a gravitational field. For instance, your feet and head actually experience slightly different gravity since your feet are closer to Earth's center. But you probably wouldn't notice unless you were really, really tall. Ow. It's the same reason water on Earth actually bulges out on the side that's closest to and farthest away from the moon, causing the tides. Essentially, gravity can squish and stretch things because of the unequal force. Around black holes, this effect becomes extreme, causing basically anything and everything to stretch and break apart. For planets and stars, once their own gravity is overcome by the black holes, they fall apart into the gas and dust that forms the accretion disk. But what happened to, say, a person? Or, say, some pasta dough? Well, the tidal forces would cause what's closer to the black hole to fall faster than what's further away, and compress the sides, essentially stretching it out into a noodle. You see where this is going, right? This process is given the very scientific name of, I kid you not, spaghettification. And just like that, dinner is served. Mwah! And hey, it's a pretty easy recipe to follow along at home, too. You just need a black hole. And believe me, the flavor is really out of this world. While black holes are known for their crushing gravity and trapping everything that enters, even light, it ends up being that same extreme environment that produces some of the brightest things in the entire universe. I like that. So what do you think? Was black holes emitting so much light and energy surprising? Would you ever want to visit a black hole? Do you suddenly have a craving for pasta? Let me know in the comments below. If you've watched this far and enjoyed, why not leave a like and subscribe to not miss out on future adventures. Of course, I'm not an expert, but I do my best to make sure everything presented is as factual as possible. Some sources are down below. As always, I've been your arbiter, and thanks for visiting the Wanderer's Expanse. Hey, there's my pasta maker!